Okay, so say we come across a problem where we have to find find the electric field resulting from multiple particles in the system. Two or more particles. How do we go about doing that? Well, first, let's make sure that we understand what the electric field being emitted from one particle looks like. Okay, so let's assume that this is the charged particle right here where my finger is. Okay, a charged particle Q, right in the middle of this page. There's an electric field surrounding this particle. This particle is creating an electric field, and that electric field is described by this equation right here. Well, this equation actually describes the strength of the electric field, or the intensity of the electric field, as a function of position. More specifically, as a function of a distance from the particle Q, r. Okay? So what this equation tells us is that E, the electric field, or E field, as sometimes I'm going to write it, is proportional to the charge itself, how negative or how positive the charge is itself, divided by the distance from the charge to the actual point where the electric field is being measured. So at different points on this page, you're going to have different magnitudes or different intensities of the electric field. Closer to the point, the electric field is going to be higher because R is smaller. So E is going to be higher because R is in the denominator. Okay, the farther away you get from the particle, the weaker the electric field is going to be. So you're going to have an electric field E1 here corresponding to R1. Okay, you're going to have an electric field E2 here corresponding to R2. Okay, you're going to have a different intensity of the electric field here corresponding to R3. Same thing for R4. You're going to have a different one there. So let's talk about some numbers. Okay, what if to make it a little bit more concrete, if we substitute, say the charge, how much is the charge? Say the charge is 2 coulombs, okay? And R1 equals 3 meters. The distance from the distance from the charge to the point where we want to measure the electric field is 3 meters. Well, then let's find out what the electric field is. Well, it's E1, where E1 is equal to KQ over R1. Okay, that's this equation just rewritten here in terms where R is now R1, a specific R. Okay, well, R1 equals 3m, 3 meters. Okay, so that's going to be, so R1 squared is going to be 9 meters cubed. Okay, and so Q is 2 coulombs, and so the electric field is going to be 2K over 9, where K is related to the electric permittivity of free space. Okay, where so K is 1 over 4 pi epsilon naught, and epsilon naught is 8.85 times 10 to the negative 12. Okay, so but the units you're going to have here for your electric field are going to be newtons per coulomb. Okay, these are units here. So that's how you calculate that, and I'll let you plug in for K. So what would be let's move on. What would be the electric field here at this point? What is it? E2. Okay, that's at R2. Well, R2 is 5 meters. It's a little bit longer than R1. Okay, so we plug in for R2. That's going to be 25 meters squared in the denominator. Our charge is still 2 coulombs. Okay, and we end up with 2K divided by 25 newtons per coulomb. That's the units of our electric field. Okay, and we do the same thing for 3. What's the electric field here? You can see it's stronger. It's 2K. How did we get that? It's, well, E3 depends on R3. R3 is 1 meter. We plug in 1 meter here, so we get 1 meter squared in the denominator. In the numerator, we get K times 2 coulombs, so that's going to be 2K newtons per coulomb. All right, so this problem we wanted to figure out. We want to understand how to calculate the electric field between one or more particles, but we wanted to make sure we had the basis here. We have basic understanding for how to calculate it for one particle, because when we do 2 particles, what we want to do is simply add the electric fields at that point where we're measuring. Okay, so I'll explain that. So the electric field due to two charges at a point between them, at an arbitrary point in between them. So here we have our 2 charges here, Q1 and Q2. Okay, and just as we had in our previous diagram, you know, we have electric fields being emitted from the charges. The charges are creating electric fields around them, and we want to find the electric field at this particular point X, which is a distance D1 from Q1 and a distance D2 from Q2. What is E1 and E2 here? We know that if Q2 wasn't here, then the electric field would be E1. We know if Q1 wasn't here, that the electric field at X would be E2. But what happens when they're both there? Okay, well, the particles are separated by a distance D. Okay, all right, the particles themselves are separated by a distance D, but the point where we want to find the electric field is a distance 1 from charge 1 and a distance 2, D2, from charge 2. Okay, well, here's the solution. Let's calculate the electric field E1 at X. Okay, well, it's just like we did before in our previous discussion of the electric field due to one charge. E1, the electric field at X due to charge 1, is E1 D1. E1 of D1. This is a function of E1 is a function of D, where E1 equals K Q1 divided by D1 squared. Okay, if we substitute in for Q1 is, say, these charges have the same magnitude. Okay, so Q1 and Q2 are the same magnitude, Q. So we replace Q1 with 2 here, and we still have D1 here. E2 at X, or the electric field due to charge 2 at X, is simply E2 of D2. Okay, which is K times Q2 divided by D2 squared. Okay, substituting in for Q2, we have K Q equals K2 over D2 squared. All right. So in general, so we're going to add. So basically, the idea is that we're going to add E1 to E2. But how are we going to add them? There's a special way we have to add them. In general, electric fields are vectors. Okay. Notice how the electric field E1 at X due to Q1 points to the right. Okay. It points to the right. And the electric field due to Q2 points to the left. What's going to happen is that they're working against each other. So the E field at X will thus be the sum of the two combined as E1 of D1, E2 of D2 plus E2 of D2, where that sum equals KQ over D1 squared minus KQ over D2 squared. Why is that minus there? Well, I just explained it. It's because they're working in opposite directions of each other. E1 is pointing in the left direction, in the right direction. E2 is pointing opposite to the left. Okay. All right. So in the case that D1, in the case that X is located halfway between the two particles, okay. In other words, D1 equals to half of D, and D2 equals to half of D, or D over 2, then what's going to happen? Alright, that's what I just explained. D1 equals D2 equals D over 2. That's X being halfway between the two particles. In this case, okay, D1 equals D over 2, D2 equals D over 2. I get the same thing minus, I get this term minus this term, which is the same term, which equals 0. Okay? So they cancel each other out at the center. At the center. Over here, it's going to be something different. Over here, it's going to be something different. But at the center, they cancel each other out. Okay? Now, suppose we had the same situation, but opposite charges. Okay? So let me redraw that. I have the same situation. Two charged particles here, separated by a distance d, except Q1 is positive and Q2 is negative. Okay, I still want to find the electric field at X in between them. Okay. All right. So we do the same. It's the same procedure, the same idea, the same concept. We add the electric fields at the point X. What is the E1 at point X? Well, it's E1 at D1. It's the electric field at a distance D1 from the charge Q1. E2 is D2 is the electric field at a distance D2 from Q2. Okay? So this is expression. This is E1 here, and this is E2. Note this charge is now negative because this is a negative charge and this is a positive charge. Okay, so I have a negative charge and it's going in the opposite direction. Two negatives make a positive. Okay, two negatives multiplied times each other gives me a positive, and so now they're working towards each other. And this makes sense. If we had a test charge here, a positive test charge here, this positive charge will be repelling it in that direction, and this negative charge will be pulling it in that direction. So you see they're working, you see they're working constructively. They're interacting constructively, these two electric fields. All right? So in the case that D1 equals D2 equals D over 2, in other words, X is halfway between the two particles, or X is at a distance D over 2, then E is going to be, we simply substitute D2N for D1. D over 2N for D1 and D over 2N for D2, and we work out the arithmetic, and you see the expression that we get. So in general, this will work for any cluster of particles, whether you've got three particles arranged in a triangle, or 4 particles arranged at the corners of a square, or 6 particles arranged at the corners of a hexagon. What you do is you just find out where you decide where you want to find the electric field at, among the particles, and then you measure the distance of each particle away from that point, and calculate the electric field using those from each particle using those distances. Okay, so I hope that helps. Okay, let me know if you have any questions. All right.